Hi guys, please like, share and subscribe. And if you want full course for any actuarial subject, visit theactuarialguy.com or WhatsApp on this number. Thank you.
Hello and welcome guys. In this video, I want to start discussing factors. So what are factors? Factors are just categorical vectors with categorical data. Now this categorical data can either be unordered, such as male and female. There's no natural ordering between male and female, right? Uh, or they can be ordered, such as survey responses, agree, neutral, disagree. Right now there is a clear ordering: agree, neutral, disagree, or you can also put it as a descending order. That would be disagree, neutral, agree, but neutral will always be in the middle, right? Or you can have insurance groups: group 1, group 2, group 3, group 4. So this is ordered categories, right? These distinct categories are called as levels in case of factors, right? Now, why would you use factors? Why not just store this data as vectors? Because you can. Vectors are just more flexible. But there are a couple of reasons to use factors. First one is factors are more memory efficient. Think about a vector: male, female, female, male, right? So on and so forth. R would be storing individual strings there as male and female, and it would not realize that these are just two categories. A much more efficient way to store this, which R uses for factors, is that you assign the value 1 to female, 2 to male, and then just store these as 1, 2, 1, 2. Essentially, the information is just condensed into binary information, if you would like to call it that, right? Just two categories, right? So that is one reason why you would use factors. Another reason is that it's very convenient for statistical modeling and plotting. So for example, if you want to run a linear regression, which is something we'll be learning in subject CS1, when you want to give categorical data into a linear regression, you essentially want to convert it into dummy variables, right? You want to do one hot encoding for it. This is something we'll learn about later. So you would want to assign value 0 to females and 1 to males, right? Something like that. And just convert it into one simple variable to put it into regression, right? R does it on its own when you provide it with a factor or data in a categorical form, right? So that is the advantage. R is able to automatically understand what you want to do with your data, right? And finally, it's very convenient for plotting because R understands that these are different levels and they should be plotted as such, and these are not treated as characters or strings, right? So that is why you would use factors, right? Now, how do you create factors? For example, you have this gender vector, which is male, female, female, male, female, female, right? So this, if you want to convert into a factor, you will be using a factor function. So firstly, let's create this gender vector. So this is your gender vector. If you will see, the values are stored as male, female. Now let's create the gender factor, right? So that will be equal to gender vector converted into a factor. So I'll type a factor function and put gender vector inside it, right? And now if you run this, you will see that R has converted this gender vector into gender factor, where it says it's just a factor with two levels and the values are stored as 2, 1, 1, 2, 1, 1. So it has essentially converted female into 1 and male into 2, right? So it says the unique values are female and male, and we have stored them as 2, 1, 1, 2, 1, 1. Now, why was female assigned the value 1 and male assigned the value 2, right? Is R a feminist? No, that's not the reason for it. It just takes the values as you know, in an alphabetical order by default, right? So because F comes before M, that is why female is given the value 1 and male is given the value 2, right? So it is just doing this in a alphabetical order. Is there another way to do it? If we want to assign 1 to male and 2 to female, how would you do that? So in order to do that, you can actually use a function which is called as levels. Okay, so I can actually assign the levels here. So I can actually define gender factor ordered, right? So now let's say I want to make this from the gender vector, right? But I want to have males as 1 and females as 2. So I will just tell it levels. My levels are that I am taking males first. So male is first and then female is second, right? As soon as I do this, okay, I will get this new factor, which is gender factor ordered, right? And you will get male first and female later, and now later. And now this is just 1 2 2 1 2 2, just the opposite of what we had earlier, because the data is the same, but this time male has been taken as 1 and female has been taken as 2. Okay, so that is how you can actually tell R what is your preference for the labels. Otherwise it will assign the labels automatically in an alphabetical order. Okay, so that is the first thing. Now let's move on from this. So you have inherently ordered data sometimes, right? For example, you have these 3 levels, which is good, poor, average. Okay, so this is health status data. Okay, so let's say you have this health status data and you have stored this as good, poor, average. Okay, now this is stored normally as a vector, right? Now I can make it a factor by just putting factor around it, right? So let's do that. So health status factor would just be this if I put factor around it. Okay, yeah. So now you see this is factors with 3 level, average, good, and then poor. Okay, so the ordering is all wrong because it is done based on an alphabetical order. In fact, if you just print this health status factor, you will get average, good, poor. Okay, the ordering is wrong because it should either be good, average, poor, or poor, average, good, right? Average should be in the middle. So R has gotten this all confused, right? So you need to tell it what the levels are and how do you want them to be ordered, right? So for that, what we'll do is we'll use something called as the ordered argument, right? In the previous one, where we were making gendered factor ordered, there is no natural ordering, so I don't need to tell R that. This argument levels I just used to tell R which one to take as 1, which one to take as 2, right? So I can do that here as well, but I'll also tell R that this is naturally ordered by using this ordered parameter. Okay, so I have taken this factor. Okay, and then I want to put 2 more parameters here. The first one is called as levels. Okay, and levels are average, good, poor. Okay, so I will say let's take the ordering as poor, average, good, and then good. Simply doing this will just make the levels as poor, average, good. Okay, but still R does not know if there is a natural ordering here, if good is better than average is better than poor. So if you want to do that, you would have to add this additional parameter, which is called as ordered, and ordered will be true in this case. Okay, so once you put this, now R knows that poor is worse than average, which is worse than good. Okay, so now if you print this, you will see it takes poor is less than average, which is less than good, and this is your data. If you try to print the structure of it, okay, if you go for structure of this factor, then what do you get? We'll be getting same thing as here. You have gotten poor is less than average is less than good, and then the values are stored as 3 1 2, 3 being good and 1 being poor, 2 being average, right? So that is how this has been stored, right? What else do we have here? Now if you want to check if the first element is better than the second element or the third element, okay, then or greater than the second element or the third element, so the value assigned to good is 3, the value assigned to the second element is poor is 1, right? So 3 is greater than 1, so this should give me true. Okay, let me just use this as my factor, right? So this should come out to be true because good is better than poor, right? So this comes out to be true. If you change this to the fourth value as well, right, that is average, good is still better than average, so you still get true. Okay, so is the first element which is good better than the or has a higher associated value than the fourth element that is average? Yes, it does, true. Okay, so that is what R is telling you. Okay, so this is also something you can do. Now how do you inspect and modify a factor? So you have some function which is called as levels, which can just be used to check the levels of various factors. So I'll just apply levels to all the factors that I have created here. So let me just start with gender factor and I will check for all of them. So if you see for gender factor, it is female male, right? And then I had my gender factor ordered. Okay, so here I have male female, it's been reversed, right? But still no ordering here because I've not said that it is ordered in the argument. Okay, here I've not said that it is ordered, I've just changed, reversed the order here. Okay, in fact let's just call this as reversed, not ordered, because that is confusing. Reversed. Okay, okay, so this is reversed, right? So this is male female. Now you have the next one, which is health status factor. It will just be, if you check the levels of it, okay, this is just average, good, poor, the ordering is messed up. But if you check the ordered version of it, then what will you get? You will get the proper ordering. Okay, so this is poor, average, good. Okay, so this is the ordered version of it, right? And I've told it that it is ordered, while levels doesn't tell you whether it's ordered or not, but it just gives you the levels in the proper ordering. Okay, if you want to see the number of levels, so the argument for that is n levels. So if you do n levels on all of these, you will see the number of levels. So for this vector, this factor, it should be 3. So this is 3. Okay, so this is something we have. Now let's just learn how to change the levels. Okay, how do you change the levels? So here in the health status factor ordered, you had 3 levels which were poor, average, good. Let's say I want to replace poor, that is the first category, with P, average with A, and good with G. Okay, so if you want to change the levels of a particular factor, then how do you do it? You just do levels for a particular factor and then you assign the new levels. So if you do this for your health status factor ordered, okay, it will just change the levels. Poor, the first level will be replaced by P, the second one will be replaced by A, the third one will be replaced by G, right? So now your levels have become PAG. Okay, if I just print this factor, you will notice that it is now GPAAGG, right? Good is replaced by G, poor is replaced by P, average is replaced by A. So that's how it works. Now let's just get into the puzzle. Okay, so let's look at this puzzle. Now if you see, it says you have received messy survey data where respondents use different text to represent the same category, right? So two categories, male and female, have been represented by sometimes male with the first letter as capital. You have male where all letters are small, you have M, and similarly for female. Okay, so firstly they're asking us to convert the character vector into a factor. Okay, and then they want us to programmatically reassign the inconsistent levels so that there are only two final levels, male and female. Okay, uh, and then they want us to display the cleaned factor and a frequency table of the results. Okay, so let's get into this. Okay, so firstly I create my messy data vector, which is here. Okay, and let's just create it. Now we convert this into a factor. So let me call that as clean data factor. Okay, or you can call it as clean data. That's it. Okay, now this is just factor applied to messy data. Okay, so I'll run both of these, right? So you have your clean data, which is a factor, but now if you see it, it's not that clean. It has 7 levels, and all of these individual data values have become labels, right? So now how do I fix this, right? So in order to fix this, what you need to do is you need to change these levels, all the F female in small letters, all of these labels to female with a capital F, and all of these male labels to male with a capital M, right? So now how do you do that? In order to do that, we will have to tell R that in clean data, what I want to do is I want to modify all the levels. So I want to take the levels of clean data, okay, which in itself is a vector. Okay, this is a vector. Levels clean data is a vector, right? It's just a vector F, F, female, female, M, male, male, right? Within this vector, I want to select all the values where levels is this levels is in. So for giving it a list and comparing it, you use in with percentage signs in this vector. In the vector, let's do it for males first. So in the vector M, male, these two values, okay, M and male, I want to change these two, just this value, male. Okay, so wherever it will find M and male, it will change it to male. And similarly, I want to do this for female. So wherever it will find this female in small letters or F, or small f, it will change that to female, right? That is what I'm telling her. Okay, so once you do this, the desired effect will be achieved, right? So now you see you just have two levels here, female and male, and female is 1 and male is 2. Okay, so this is how you change it. Okay, and now if I just want to print levels, sorry, not levels. If I want to print the whole clean data, you will see it's actually clean, right? So you have male, female, female, male, right? All of the values earlier, male have been replaced by male in a proper format, and female have been replaced by female in a proper format, right? Now, if you want to print the frequency distribution of this data, you can also do that to check how many males and how many females you have. Here you can obviously count them, but if you had a bigger data set, you might want to look at the frequency distribution. So the uh, function used for that is table. Okay, and you apply table to clean data. So you have 4 females and 4 males. Okay, so this is how you check the frequency distribution. This is all that the question asked us to do. Let's move. Okay, next I want to talk about matrices. So you know what matrices are. They are basically two-dimensional arrays, but they contain the same data type in case of R. Okay, so now let's explore the matrix function first. Okay, so let's just get some help on the matrix function, right? So if you'll see, matrix has a couple of arguments. The first one is the data. So you put in the data. Then you have n row, which is the number of rows. Then you have number of columns, and then you have by row, which is by default false, which means how do you want to start populating the matrix, whether you want to populate it by row or by column. By default it's false, so you would be populating vertically, right? We'll see what that means. And then you have dimension names, okay, which is basically a list of the row and the column names. So we'll see how you provide this as well. Okay, so let's just dive right into it. How do you construct a matrix first of all, right? So let's construct a matrix M1, and I will pick this up from here, from my notes itself. You see this matrix M1, the data is from 1 to 6. Okay, the n row argument is 2 and n column is 3. So it will create a 2 cross 3 matrix taking the values from 1 to 6, 1, 2, 3, 4, 5, 6. Right, so that is what it will do. Let's run this. So you will see this is your matrix, and if I print this, let me print this M1, it is just 1 2. So see, because by default your by row argument is false, it gets populated vertically, 1 2 3 4 5 6, right? That is how it works. Okay, let's move on. uh, so this is how you populated it by row. Now let's try and populate this by column. Okay, so I want 1 2 3 4 5 6, right? That is by column, by row. Okay, this was populated by column, now we'll populate it by row. So I will just change one argument, that is by row, and I will put this as true instead of false. So it will start populating horizontally through rows. Okay, so now if I print M2, you will see it is 1 2 3 4 5 6. So it's going horizontally. First the first row is populated, then the second row is populated. In the case of by column, what did it do? It, or by row false, it just populated first column, second column, third column. So that's how it works. Now after that, what else do I want to see? Okay, how do you convert vectors into matrices? Let's look at that, right? So let's say I have two vectors. So this is vector 1, which is equal to C1 comma 2 comma 3, right? C is the combined function through which you create vectors, right? And V2 is C 4 comma 5 comma 6, right? So this is what you have, and now you want to either stack them horizontally or you want to stack them vertically. So if you want to stack them through rows, you use R bind. Okay, R bind, that is row binding. Okay, V1 comma V2. Okay, so now these would be bound as rows. Okay, so this is your M3. M3 is equal to this. Okay, so you see, oh, this is not made yet. Okay, let's make. let's run this together. So now if you'll check out M3, what do you have? You have 1, 2, 3, first row, 4, 5, 6, second row. Okay, so that's how you horizontally bind these. Now you want to vertically bind them. So that will be your M4. M4 is C bind. We use C bind. And then again you do V1, V2. Okay, two vectors vertically stacked. Okay, so M4 is 1, 2, 3, 4, 5, 6 vertically, right? So that's how it works. Then I want to talk about how do you get the dimensions of any matrix. So for any matrix, if you want to get the dimensions, the function is dim. So if you want to check the dimensions of M1, it is 2 cross 3. That is 2 rows and 3 columns. If I look at M1, you will notice M1 was here. Okay, 2 rows, 3 columns, 2 comma 3. Okay. Similarly, if you want to check the dimensions of, let's say, M2, the dimensions there were again 2 comma 3, right? Because we had specified them to be the same. If you will see, yeah, this one M4 is 3 comma 4, 3 comma 2, right? Because you have 3 rows and 2 columns. Okay, so that is your dimensions function. Then how do you check the number of rows and number of columns? So n row gives you the number of rows. Okay, so that's 3 in case of M4, right? 3 rows, 1, 2 and 3, right? And similarly n col will give you the number of columns, right? So number of columns is 2 here. Okay, then you have row names and column names. So you can assign row names and column names. Okay, let's say I want to assign row names and column names. So there is an argument called as row names. Okay, and you want to assign row names to M4. Okay, now how many rows did M4 have? 3 rows, right? So you want to assign 3 row names to it, right? Which will be, you write them as a vector. They can be A, B and C. Okay, and you want to assign column names as well to M4. Okay, so there are 2 columns here, X and Y. Okay, so this is how you assign them. Firstly, let's assign row names and check out M4. So M4, if I check out now, you will see that A, B and C row names are assigned. V1 and V2 are column names because it has just taken those vector names by default, right? If I change the column names after this, you will see X and Y are the column names. So these are your column names. That's how they work. Then how do you fetch a particular value from a matrix? Okay, let's say I want to get from M4 the value in the third row and the second column. So that is M4 3 comma 2. So if you look at M4 now, this is your sixth, the value is 6, right? Third row, second column, third row, second column, right? So this should give me 6. So this comes out to be 6. Another way you can fetch this value is by saying, look, I want to fetch based on the row name and the column name. So it's the value at A comma C comma Y. Okay, so this is again 6. If you fetch at A comma X, that will be 1. A, right? So that's the first row and X is the first column. And if you give it a wrong argument, then it will just tell you, I have no idea what you're talking about. Okay, subscript out of bounds. Okay, so this is how it works. Okay, then if you want to fetch the entire first row, so it will be M4 and I want to get the first row, so I'll do first and then I'll just put a first row comma 1 comma. So it's the entire first row, which is x and y have values 1 and 4, right? That was the first row. See, 1 and 4, right? If you want to fetch the entire first column, you say comma 1, okay? Because the second argument is the column, the first argument is the row. So you leave the row blank, you just tell it to fetch the first column, which is the values in all three rows 1, 2, 3, right? So you see this is the entire first column 1, 2, 3, okay? It will still come horizontally because it comes out as a vector. So that is that. Now what I want to do, let's say you want to fetch from M1 or from M4 itself, you want to fetch the first and the second rows, okay, and the first and the second columns, okay? So it should give 1425, right? 1425 should come. You've just taken the first two rows and first two columns, okay? So this is 1425, okay? So that's how it works. That's how you get couple of rows and couple of columns in a range, right? So that's how you can specify them. Then let's talk about matrix arithmetic. So if you want to add up two matrices, right? So let's say you have your M5, which is defined as matrix from 1 to 6, and I want to have n row as 3, n col as 2, okay? This is my first matrix. So that's M5 for you, and then let's define M6, which is just matrix, and I will take instead of going from 1 to 6, I will still instead go from 7 to 13, right? And then the dimensionality is 3, 2, right? So that's M6 for you. 7 to 13. Oh, it should be 7 to 12, not 13. Yeah. So that's M6 for you. Okay. We got this warning because if you take 7 to 13, that's 7 numbers, not 6, right? So the number of values that you put in should match the dimensionality. It should be a multiple, or it should actually be equal to whatever is the product of your n row and n column, right? So you have M5 and M6. Let's look at both of them. So this is M5 and this is M6 for you. Now, if you add up the matrices, what do you get? M5 plus M6, which would be equal to element by element addition, right? So 1 and 7 add up and become 8. 2 and 8 add up and become 10, and element by element they have been added, okay? What if you multiply the matrices? What if you do M5 star M6 or M5 asterisk M6? Ideally, you would expect that this would lead to the matrix multiplication, but that is not the case. Actually, it leads to element by element multiplication. So you would see that here 7 times 1 is 7. Then here you would notice element number 2 comma 1 is 8 times 2, that is 16. And then if you will see element 3 comma 1, that is 3 times 9, right? M5 times M6, so 3 times 9, that is 27. So you will see that all of these elements are just element wise products, right? So when we want to do matrix multiplication, this is not what we are intending. In fact, this product sign, this star sign or asterisk sign, is a representation of the element wise multiplication, right? If you want to do matrix multiplication, then the notation is percent star percent or percent asterisk percent, and then you can just write M5 and M6 here. This will give you the matrix multiplication, okay? Now we are getting this error, which is non-conformable arguments. Reason for this error is that for matrix multiplication, you have a condition that the columns of the first matrix should be equal to the number of rows in the second matrix, right? So if you are multiplying two matrices, if you have A cross B, you can only multiply it with the matrix that's of the dimension B cross C. That is, the columns here should be the same as the rows here, right? So here M5 and M6 cannot be matrix multiplied. So in order to fix this, what I'll do is I'll define M7, which will have the same number of rows as the number of columns in M5. Okay, so how will I do this? So instead of taking 3 comma 2, I can take it as 2 comma 3. So once I take this as M7 as elements from 7 to 12 and the dimensions are 2 comma 3, if you look at M7, it will now have 2 rows and 3 columns, right? And your M5 had 3 rows and 2 columns, right? So now the second element of M5, basically the n call of M5 is same as n row of M7. So now they can be multiplied at a matrix level. So let me see M5 times M7 matrix multiplication. So you get your result as this, and you can also do M7 cross M5, right? When you do M7 cross M5, you will get a 2 cross 2 matrix. When you do M5 cross M7, right, you get a 3 cross 3 matrix, right? Because here the number of elements is 3 cross 2 and the number of elements in M7 is 2 cross 3. So the result is this 2 gets eliminated, it's 3 cross 3, right? And here it's 2 cross 3 for M7 and then cross 3 by 2 for M5. So you get a result of 2 by 2 when these two get eliminated, right? So that is the idea. This is how it works. Now there are other matrix functions that we can use. For example, transpose. So you can take a transpose of M5. M5 currently, if you look at it, is a 3 cross 2 matrix, right? So if I take a transpose, the rows will become columns and columns will become rows. So you see this has just been transposed, right? So my first column was 1, 2, 3. My first row now is 1, 2, 3, right? My second column was 4, 5, 6. Second column is 4, 5, 6, right? This is your transpose. Then you can get the determinant of M5, right? Determinant you can only calculate for a square matrix, right? So now I need to define a new matrix. Let's call it M8, which is matrix. I will take the values from 1 to 4 and the rows are 2, columns are 2. Okay. So this is your M8. This is a 2 cross 2 matrix, and now I can calculate the determinant, which comes out to be -2. Okay. Then you have, if you want to find the inverse of a matrix, right? So you use the function solve in order to get the inverse, and solve M8 gives me the inverse of M8, right? Which is this. If you want to solve the equation AX equals B, right? This is a system of linear equations we used to define in this format, and here your A is ideally n cross M matrix. Okay, that's the dimensionality of this. Your X is a vector of dimension M. Okay, so its dimensionality is M, and B is a vector of dimension, this is M cross 1. So the resulting dimension would be n cross 1, right? This is how it is defined, right? So for example, you have 2 to 3 equations. Let me just define 2x plus 3y is equal to 7. This is your first equation. The second equation is 5x plus 4y is equal to 9, right? So now how will you write these matrices and vectors? So A would be defined as, let me just write it out for you. So it's matrix, so 2 comma 3 comma 5 comma 4, okay, and I want this by row, okay. So this is a 2 cross 2 matrix and by row is equal to true. This is how it works, okay. So this is your matrix A. So if you look at A, it's just 2 3 5 4, okay, 2 3 5 4. This is how you define it. Then you have X, which is just equal to, so this is 2 cross 2, this should be 2 cross 1, right? So it will be equal to x1 comma x2, okay. That is how X is defined. And your matrix B would be defined as C vector, right? You can assume that this is 2 cross 1, but I'm just defining it as a vector. So now in order to solve this equation, you need to do solve A comma B in order to get these values of x1 and x2. So you get your answer as these two values, okay. So that's how you solve an equation. If you want to get eigenvalues and eigenvectors of a square matrix A, you can do that by using the function eigen A, okay. So this is your eigenvector and this is your eigenvalues. Now what are eigenvalues and eigenvectors? So if you have a, for a given matrix A, if you are able to define a vector A times V is equal to K times V, where V is a vector, A is a matrix, and K is a constant, okay. K is a scalar, okay. If you are able to do this, then K is equal to the eigen value of A in the direction of V, and V is equal to the eigenvector. Essentially what we are able to do is all the information that is contained in A, you are able to separate out the magnitude and the direction of that, okay. For any information in a vector space, there are only two parts to it. One is the direction of it and the other one is the magnitude of it, right? So this is called as eigen decomposition. What we are doing is we are able to separate out the magnitude into K, and we are able to separate out the direction in terms of V, okay, which is a vector. So these two together are able to capture all the information that is there in A, okay. So that is the idea of the eigen decomposition. Now this is very, very useful in our course for principal component analysis. So I'll visually explain this entire idea to you there, right? How does this exactly work? What eigenvalues are, what matrices are, eigenvectors are, and how do we use them, right? So all of this we cover there. For now, you just need to know this, that you're able to take all of the information from a matrix and separate it out in terms of a scalar, that is the scale or the magnitude of this information, and in terms of a vector, which is the direction of this information, right? And this eigenvector, the scale of this is actually 1. Okay, so the modulus of v, it doesn't have a scale, so mod v is equal to 1. So it just contains the direction, right? And k just because it's a scalar, it just contains the magnitude. Okay, so this is how this works. Let's move on. Okay, now let's look at this question. So it's the investment portfolio puzzle. An analyst is reviewing a new investment portfolio that consists of three shares of three tech companies: Alpha Tech, Beta Corp, and Gamma Incorporated. The analyst has the following summary information. The total investment cost for the entire portfolio was $50,000. The portfolio generates a total expected annual dividend of $1,550, and a risk analysis matrix calculated as 2 times share of A, 1 time shares of B, and 3 times shares of G results in a total risk score of 2400. So these are our three equations that are given in a way. I will actually write it out and show it to you. How do you make turn these into equations? Here is the per share information for each company. So for A, we have got price per share and dividend per share, and similarly you have for B and the company G, which is Gamma Incorporated. Now your task is to determine how many shares of each company, shares A, shares B, and shares G, are in the portfolio. This is what we want to do. Okay, so what is happening here? Let me just write this out, the problem out for you, because it would have been a while for most of you, since you would have done matrix algebra, and this is a core matrix algebra problem. So what is happening here? Let me just define the problem for you. We actually want to just solve three linear equations. That's what we are trying to do here. Okay, so these are the three equations that I want to solve. The first one is the cost of the portfolio equation, which is 50 is the price per share for company A. For company B, it's 100, and for company G, it's 25. So when you add up the total cost of the portfolio, it should be 50,000. That was the first piece of information that was given, right? Secondly, you had the dividend equation. Company A gives a dividend of 2, B gives a dividend of 1.5, and G gives a dividend of 1. The total dividend received is 1550. And then the third equation comes from the risk analysis matrix, which is 2A plus B plus 3G is 2400, which is your risk matrix. So these are the three equations that you want to solve. Here, if you write it in a matrix form, and what you want to do is AX is equal to B. Okay, this is what the system of equation. Now what are A, X, and B? Let's write that out. So A is equal to 50, 100, 25, okay, 2, 1.5 and 1, and 2, 1 and 3. Okay, this is your A. Your X is defined as, so this is your 3 cross 3 matrix, right? Your X should be 3 cross 1, right? So it should be 3 rows and 1 column, right? So this is defined as A, B, and G, which is what you want to solve for. And then finally your B matrix, vector B, which will again be the result of these two. If you multiply them, that will also be 3 cross 1, is just 50,000, 1550, and 2400, right? So this is how your vector B is defined, right? And this is what we want to solve. We want to solve for X such that Ax is equal to B. This is what your problem is, right? Now the way to solve this equation is, one way to solve it is X will be equal to A inverse B. right? Once you send A on the other side, you will get A inverse, right? Now the dimensionality of A inverse will also be 3 cross 3 and D will be 3 cross 1. So you can multiply these two, right? And one consideration is that in order for a valid solution to exist, determinant of A is equal to or is non-zero. If you have determinant of A as 0, then you have infinite solutions to this problem or no solution at all. Then the problem becomes meaningless. So for a meaningful solution, you need determinant of A to be not equal to 0. So now there are two ways to solve this. One way is to obviously go via the first principle, which is to find x by taking A inverse times B, ensuring that the inverse exists, which would mean that the determinant should not be equal to 0, right? So this is the first principle way. The second way to do this is just to directly use the solve function in R, where you will take solve A comma B, and that will just give you the value of x. Okay, so we'll do it via both the methods, right? And see if we get the same answer, right? So that is what we are going to do. Okay, perfect. Now let's just try and solve this. So I want to solve this. I will add a new script, and yeah, let's start with this. So I need to first define my A, which is something I had already written for you. So A will be equal to C, okay, 50, 100 and 25. Okay, that's the first three values. 2, 1.5 and 1, and finally 2, 1 and 3. Okay, these are the values. You want to take the number of rows as 3, number of columns as 3, and you want to take the by row argument as true. Okay, so this is your A, and this is obviously inside the matrix function, right? So A is defined as this matrix. If I print A, you will see that it looks like this, which is what we wanted, right? I've taken by row as true because I wanted to go 50, 100, 25. So I wanted to go by row 2, 1.51, so on and so forth, right? Similarly, I'll just define B as well, which in this case is just C, and the three values, which will be 50,000, 1550, 50,000, 1550 and 2400. Okay, so this is also defined, right? So these are the two things you have. Now what is the question asking for? Let's just look at that. Yeah, so here first thing, yeah, we've been able to do this. We've been able to create A and B. Now they want us to calculate the determinant of A, and what does this tell us about the system of equations? So determinant of A, you can just say maybe x, or you can call it det, is equal to determinant of A. Okay, so this is your determinant, and if you print the determinant, this is equal to minus 250. So this is non-zero. Okay, let me put proper comments since this is a puzzle. So the first thing is defining the matrices. Okay, calculating and determinant of A. Okay, so this is non-zero. Determinant means that A inverse exists and that the system of equations has a unique solution. Okay, so this is what you can conclude. Now what is the next part? uh let's just see. So yeah, let's calculate the inverse of A and store it in A inverse. Okay, so that's what they want us to do. So A inverse is equal. The function that we had learned was solve. Yes, to calculate the inverse of A we use solve. Okay, so solve, right? So inverse of A can just be printed now. So you can say uh, inverse of A equals solve A, or you can say A inverse, right? So inverse of A is equal to this. Okay, so you have your inverse of A. They also want us to calculate the transpose of A. Okay, so the transpose of A is equal to A T. They want us to save it in EAT, so that will be T of A, right? That was the function. Yeah, that's correct. So that is your T of A, and if I print AT, that is just this. Okay, so you have both inverse and transpose. Now I want to solve this system of equation, right, by using the two methods, right? Method 1, using solving equations using solve. Okay, so x will be equal to, your result is solve A comma B. Okay, so if you print x, so you just see this. So it's 405, 180 and 470. So you can say the following, you can use the cat function, cat. Okay, and you can say the following number of shares will be bought for A, B and G, and that is X. Okay, and then you can also put respectively here, right? So the number of shares bought for A is 405, B is 180 and G is 470, right? And now we need to verify this using method 2. So method 2 using first principles, right? First principles. So X now will be equal to uh, A inverse times B, right? And you have to use matrix multiplication. So you do this. Okay, so this was X, this I can call it as X2, right? So this is your X2, and if you print X2, here again same thing you will print. So is X and X2 the same? Yeah, it comes out to be the same. So to verify, you will say verification. You can write paste or cat. Both of the functions work the same. You can either use paste or cat. I'll show you how to use paste. Are the results, is the solution the same using
both methods. So you can check if x1 is equal to x, that is x2 is equal to x, right? So this you can print, uh, and oh, you're getting three results because it's comparing all three values, and for the first two values it's false, the third value is true because there might be some difference in decimals. So you can actually check using a different function which is called the all equal, but all equal only applies to objects which are of the same type, right? So here both of them either need to be vectors or matrices, right? uh, if you just check the help on all equal, uh, it's able to check if x and y is a utility, compares our objects x and y testing near equality. If they're different, the comparison is still made to some extent, and a report of difference is returned, right? So for all, to apply all equal, you need the object type to be similar. So here, if you just check the type of x2, it's stored as a matrix, but x is stored as a vector. So you need to make x2 as a vector as well, uh, in order to just execute this, right? So I will do as vector x2, and then x as it is because that's already a vector. And yeah, now this will check if the solution is same using both the methods, and I'll get a true. So is the solution the same using both the methods? Yes, true, because these two solutions are the same, and we have seen that x2 and x are just the same uh, solution, right? So yeah, that's how this works, and that's how you solve such a question. Thank you.